Number 4, the figure above shows the graph of f prime on the closed interval from -1 to 5. The graph of f prime has horizontal tangent lines at x equals 1 and x equals 3. The function is twice differentiable with f of 2 equals 6. Again, they always throw something like that in there. Going to end up being important, I'm sure. Find the x-coordinate of the points of inflection of the graph of f. Give a reason for your answer. All right, taking a look at A. Find the x-coordinate of each of the points of inflection of the graph of f. So this again is the graph of f prime. So the second derivative, f double prime, would be graphing the slopes of f prime. So if f prime is increasing from here to here, f double prime should be some kind of positive from there to there. If f prime is decreasing from here to here, f double prime should be negative from there to there. And then it's increasing from here to here. F double prime should look something like that. Makes sense. If f prime has 2 humps, f double prime should have the 1 hump. So points of inflection happen when f double prime equals 0, and it goes from positive to negative. So we found 2 of those. Point of inflection at x equals 1, because f double prime goes from greater than 0 before it to less than 0 after. And again, it happens at x equals 3 for the same reason. So B says, where is the absolute minimum and maximum over the interval? So we can kind of roughly sketch in the graph of f. F of 2 is 6 was given. So that's somewhere up here. Now, from there, the slope of it has been negative the whole way. So it's been decreasing to get to there. Still, the slope is negative until 4. So it should be decreasing until 4, and then increasing after 4. Therefore, the absolute minimum has to be at x equals 4, because the graph is decreasing the whole time and then switches to increasing. Then let's look for some explanation on the absolute maximum. We discussed that because the derivative is negative the entire time until 4, it is decreasing. So our maximum, and then it does increase from 0, let's grab another color. It does increase from 0 to 5. The derivative is increasing. So the maximum is either at the beginning, x equals -1, or at x equals 5. It is enough justification to say that based on the graph, that area is much less than this area. Therefore, the absolute max must be at x equals -1. Now your justification in here could be something to do with the integral from -1 to 4 of f prime. You know, that guy is much greater than the integral from 4 to 5 of the same function, which seems clearly obvious from our graph here. And part C gives us g be the function defined by g of x equals x times f of x. Find an equation for the line tangent to the graph of g at x equals 2. Okay, when we say the word tangent line, we have got to write down y equals m x minus x1 plus y1. Then we could put in for sure our x value. What's my x value going to be? It's at the point x equals 2. Put 2 there. All right, now, first time in our 2004 test that we get to use our fun derivative tools. To find the slope, we need the derivative at that point. So g prime of x is equal to our product rule, the derivative of the first times the second plus the first times the derivative of the second. So to find g prime of 2, we're going to need f of 2 plus 2 times f prime of 2. F of 2 was given in the initial condition. F of 2 is 6. So g prime of 2 is 6 plus 2 times f prime of 2. F prime of 2 right there is negative 1. So that is 4. So I'm going to go ahead and put my 4 right there. Good. So the only thing we need left is what was our y value. To find g of 2, we need 2 times f of 2. Again, f of 2 is 6. It actually showed up twice in this problem. So g of 2 is 12. Then we can put our 12 right there. So I could probably clean that up a little bit. Y equals 4x minus 2 plus 12. Little product rule derivative, plugging numbers in. We got this. Calculus.